Vibration analysis to noise. In vibration analysis, understanding the impact of interference on signal clarity. Introduction to noise, sources of noise. Noise in vibration analysis refers to non-periodic, random, or impact-based vibration signals that do not follow a predictable sine wave pattern. Unlike harmonics or synchronous signals, noise is characterized by irregularity and unpredictability. It can originate from mechanical processes such as cavitation, turbulence, or intermittent impacts, and often manifests as a raised noise floor in the vibration spectrum. This elevated baseline makes it challenging to identify discrete peaks associated with specific machine components. Understanding noise is critical because it can mask fault signatures or indicate early-stage mechanical issues. Analysts must recognize that noise is not always harmful. Some sources, like fluid turbulence, may be normal, while others, such as cavitation or bearing defects, require immediate attention. The ability to differentiate between benign and harmful noise sources is essential for accurate diagnosis and effective maintenance planning. Noise in machinery can arise from several sources, each with distinct characteristics. Single impacts or transients occur when components momentarily collide, producing sharp spikes in the time waveform and broadband energy in the spectrum. Random vibration often results from process turbulence, cavitation, or irregular fluid flow, creating a continuous, non-repetitive signal. Cavitation in pumps is a common culprit, where vapor bubbles collapse against impeller surfaces, generating high-frequency noise that can damage components over time. Bearing defects, especially in early stages, produce random high-frequency vibrations before discrete fault frequencies become evident. Structural looseness and rubbing also contribute to noise by introducing intermittent impacts and chaotic motion. Identifying these sources requires careful analysis of both the spectrum and time waveform to distinguish between normal operational noise and indicators of mechanical failure. Let's see vibration spectrum chart for noise conditions provided. The diagram above represents typical frequency spectra used in vibration analysis to identify different noise characteristics, exactly as encountered in real machinery diagnostics. What each chart illustrates. Number 1, no noise. Clean spectrum with a single dominant peak, such as 1 times RPM. This represents a healthy machine with minimal background vibration. Number 2, low amplitude scale, very low noise. Minor broadband activity visible due to measurement sensitivity or electronic noise, but still a clean machine condition. Number 3, haystack. A broadband mound around running speed, commonly linked to bearing wear, lubrication issues, or early surface roughness. Number 4, raised noise floor, cavitation. Uniform broadband elevation, often strongest at higher frequencies, typical of pump cavitation where vapor bubble collapse excites wideband energy. Number 5, raised noise floor, flow noise. Broadband noise biased toward mid to high frequencies, associated with turbulence, valve throttling, or high-velocity fluid flow. Number 6, raised noise floor, resonance. Broadband excitation amplified at a structure's natural frequency, producing uneven noise peaks, indicative of structural resonance. Noise in the spectrum, role of time waveform in noise diagnosis. In the frequency domain, noise appears as a raised baseline or noise floor across a wide frequency range, often referred to as a haystack pattern. Unlike discrete peaks that indicate specific forcing frequencies, noise manifests as a broad increase in energy without sharp lines. This makes it difficult to isolate individual fault signatures, as the elevated noise floor can obscure critical diagnostic information. The presence of noise can indicate random mechanical activity, such as cavitation or turbulence, or early-stage bearing damage. Analysts must be cautious when interpreting spectra with high noise levels, as they may misattribute the source or overlook developing faults. Comparing spectra over time and across multiple measurement points helps determine whether noise is stable, increasing, or associated with specific operating conditions. While the spectrum provides a frequency-based view of vibration, it cannot reliably distinguish between random noise and impact-related events. The time waveform is essential for diagnosing noise because it reveals the nature of the signal. Random noise appears as irregular fluctuations without a repeating pattern, whereas impacts manifest as sharp, high-amplitude spikes. By analyzing the waveform, analysts can determine whether noise originates from benign sources like turbulence or harmful conditions such as looseness or rubbing. Combining spectrum and waveform analysis ensures accurate interpretation, enabling maintenance teams to prioritize corrective actions effectively. This dual approach is particularly important when noise masks fault frequencies or when the spectrum alone suggests broadband energy without clear causation. Mechanical conditions creating noise, interpreting noise correctly. Several mechanical conditions contribute to noise in vibration signals. Pump cavitation is a primary source, where vapor bubbles collapse violently, producing random high-frequency impacts that elevate the noise floor. Structural looseness and rotor stator rubbing generate intermittent impacts, creating both broadband noise and transient spikes in the waveform. Early-stage bearing defects introduce irregular forces as rolling elements interact with surface imperfections, resulting in high-frequency noise before fault frequencies become prominent. Fluid turbulence and flow instability also produce continuous random vibration, which may be normal in certain processes but can complicate fault detection. Understanding these conditions helps analysts differentiate between operational noise and indicators of mechanical degradation, ensuring timely intervention and preventing catastrophic failures. Correct interpretation of noise requires a comprehensive approach that considers both its source and impact on machine health. Analysts should determine whether noise is harmful or benign by comparing measurements across different operating conditions and trending data over time. A stable noise floor may indicate normal process variability, while an increasing noise level often signals developing faults such as cavitation or bearing wear. Using multiple measurement points helps localize the source, and waveform analysis confirms whether the noise is random or impact-driven. By integrating these diagnostic techniques, maintenance teams can avoid unnecessary repairs for harmless noise and focus on addressing conditions that pose a risk to equipment reliability. Importance of Rule 3 in vibration analysis. Rule 3 emphasizes the significance of noise in vibration analysis and its potential to obscure critical diagnostic information. Noise can mask fault signatures, mimic other vibration patterns, or indicate early-stage mechanical issues. Analysts must use both spectrum and time waveform analysis to accurately identify noise sources and assess their impact on machine health. Understanding noise enables proactive maintenance, reduces the risk of unexpected failures, and ensures that corrective actions are based on accurate data. By applying Rule 3 effectively, vibration analysts enhance the reliability of condition monitoring programs and contribute to improved operational efficiency.